Hello, pre-algebra students, and welcome to Chapter 9.5, which is all about real numbers. You're probably wondering, haven't we been talking about real numbers all along? Well, maybe. Let's explain this special category. In Lesson 5, you learned that a rational number is a number that can be written as a quotient of two integers. So examples of rational numbers would be integers themselves. And within that, whole numbers. So let me draw a little picture here. So we have whole numbers, which are a type of integer, and integers are a type of rational numbers. This section, however, is also going to talk about irrational numbers. So an irrational number is not a number that can't be reasoned with, though it would be pretty funny if it were. An irrational number is a number that can't be written as a quotient of two integers. The decimal form of an irrational number is not going to terminate, meaning it's never going to come to a natural end, and it's also not going to repeat. For example, pi is an irrational number. So when we look at this chart, we have rational numbers and irrational numbers, and these are what we would call real numbers. So real numbers consist of all rational and irrational numbers, and this diagram shows their relationships. This example from your textbook is going to help us to classify some real numbers. So in our first example, A, we have the fraction 5/8. If you convert 5/8 to its decimal form, we get 0.625. That goes in evenly. That means we have a terminating decimal, and therefore this is a rational number. Looking at example B, the fraction 5/6, when we divide 5 by 6 to convert to decimal form, we end up with a repeating decimal, 0.83333, repeating to infinity. Because it's repeating, this is a rational number. Looking at example C, we have the square root of 19. The square root of 19 is 4.35889894, on and on and on. This decimal does not terminate, and it does not repeat. Therefore, the square root of 19 is an irrational number. Here's your first set of checkmate problems. For each of these numbers, please state whether it is rational or irrational. Press pause while you work. We're going to learn to graph irrational numbers next. Even though it's non-terminating and non-repeating, it is possible to graph an irrational number on a number line. For instance, if you wanted to graph the square root of 2, as we're doing in this picture example from the text, you would draw a right triangle with one leg on the number line and each leg with a length of 1 unit, as we're shown here. The reason we know to use 1 unit is because the Pythagorean Theorem tells us that the square root of 1 squared plus 1 squared equals the square root of 2, right? So that's how we know each of the units should be 1 unit long, or each of the legs should be 1 unit long, excuse me. It's kind of tricky to show you this step on the video. I can show you in person, but you can then use a compass to draw the length of the hypotenuse by lining up your compass and use the compass to draw that down onto the number line. So you'll see that our point lands just about here, which is pretty close to 1.4. If you were to use your calculator to find the square root of 2, you would see that the square root of 2 is approximately equal to 1.4. So those forms match. So both the location on the number line and the calculated answer are pretty close. Let's compare some real numbers. If we were to compare the square root of 2 and 9/5, would the square root of 2 be less than, greater than, or equal to 9/5? We're going to use a number line to define that. So here's our number line. We know from our previous example that the square root of 2 is approximately equal to 1.4. So I'm going to go ahead and graph that in right here, 1.4, and that's roughly the square root of 2, correct? Not exactly, but roughly, the best we can do. Now, if we're to calculate 9/5, that's going to be approximately equal to 1.8. And you can figure that out by simply taking 9 divided by 5 on your calculator or by hand. And that's going to be roughly equal, as I said, to 1.8. So here is 9/5. So our number line shows us that since 9/5 is to the right of the square root of 2, that the square root of 2 is less than 9/5. Just as when we were using simpler numbers, using a number line to compare value will always work. If a number is to the left, it is less than. If a number is to the right, it is greater than. Now let's try to order our real numbers from least to greatest. So our numbers are 4/3, negative 2.8, the square root of 3, and negative square root of 5. So whenever you're asked to compare numbers that are represented in different ways, for example, we have a fraction, we have a decimal, we have two numbers under radicals, I would urge you to rewrite these in the same form before comparing. So I think the easiest way to compare these is to put them all in decimal form. So to make our job easier, I've converted each of these numbers into decimal form. 4/3 becomes 1.3 repeating. Negative 2.8 stays the same. The square root of 3 becomes 1.73200508, and it continues on. It is irrational. And the negative square root of 5 becomes negative 2.236, and so on and so forth. It is also irrational, so it's non-terminating and non-repeating. All right, let's go ahead and graph these on the number line so that we can put them in value order. All right, here's our number line. Let's go ahead and place these numbers. So negative 2.8 will land right around here. Oops, that decimal point doesn't want to show up. There we go. Negative 2.236 will be roughly around here. Let's put that as a negative square root of 5. That's easier to write in this space. Then our next number is 1.3 repeating. So that'll land right around here. So that's our 4/3. And then we have our square root of 3, which is 1.73. And that goes about right here. So placing our numbers from least to greatest, our value then is negative 2.8, negative square root of 5, 4/3, and the square root of 3. And here's your next checkpoint. Copy and complete each of these statements using a less than, greater than, or equals to sign. Remember, if you're not sure how to compare these two numbers, you can always use a number line. And it is really helpful to rewrite the numbers into the same form before trying to compare them. Press pause while you work. There is one final example to complete after these checkpoint problems. In this last example, we're going to use irrational numbers for a real-world problem. Imagine that we are visiting Chicago and checking out some historical landmarks. So outside of the Washington block, we're going to divide into two groups. Group A is going to go about 800 meters to the east and 200 meters to the south to get to the Chicago building. Do you see their path? It's here in red. Now Group B is going to go about 600 meters south and then 200 meters to the east to get to the Rookery building. So to the nearest 10 meters, how much farther is Group A from the Washington block than Group B is? So in other words, who went farther? And we're going to measure that using the hypotenuse, which you know we're going to find by using, yes, indeed, the Pythagorean Theorem. So Group A is going to travel this far. Let's see, we have one leg being 800 meters squared. The other leg is 200 meters squared. So we're going to find the square root of that. And that's going to equal our total distance, which is going to be the square root of 680,000. That is roughly equal to 825 meters. All right, let's calculate group B. So group B, we have a distance of 600 meters squared, plus 200 meters squared. So we know they didn't go quite as far because we only have 600 plus 200, right? So let's see what that number is going to be. It is 400,000 meters, which is roughly equal to, the square root of that is roughly equal to 632 meters. So returning to our question, we wanted to know, to the nearest 10 meters, how much farther is group A from the Washington block than group B? All right, well, if group A went 825 meters and group B is 632 meters, then it looks like we're approximately 193 meters farther if you were in group A than if you were in group B. So the final answer is group A is about 190 meters, because remember, we're supposed to go to the nearest 10 meters. Group A is about 190 meters farther from the Washington block than group B is. That brings us to the end of this section on real numbers. I'll see you tomorrow for some more practice.